right? Or tomorrow night, I mean? Yeah. I said tonight. I said the wrong day. It's tomorrow night. What questions do you have? Yeah, we did. Because 6.3, I'm going to do another example like stuff that we've done, but we did finish pretty much everything that's in there.
You have to know the co-function identities. Do we need to memorize those as well?
You'll need to know those, yeah. Yeah, so remember those are, if you've got sine of theta, that's the same thing as cosine of pi over 2 minus theta. Or if you have degrees, you could replace this with 90 degrees as well, right? So anytime you've got a co-function, yeah, it's the complement idea. So if you had, say, if it asked you the sine of maybe pi over 5, I think they use some goofy one fractions like that on some of the Hall twins, right? Then if I replace this with cosine, then I would have pi over 2 minus the pi over 5. And then you have to get a common denominator. So the common denominator here that works is pi tenths. So then you would have cosine of 3 pi over 10. And remember again, those co-function identities come about from the fact that the opposite side in the triangle for the angle is the same thing as its adjacent side for the complement. So that's where all those come from. So yeah, we're gonna have a whole list of things to remember by the time the semester's over. So get started early with some of those. Yeah. So the co-function identity is one of those. What's that?
Chapter 7.
Yeah, chapter 7 is a bunch of identities. Yep. Other questions? I do want to do one more. It was kind of like one on the quiz, but it goes, we did one right at the end of class last time as well. So let's do, as an example, before we get into the graphing stuff, let's say that you know that the secant of theta is negative, well, let's say 41 over 9, and let's say the cosecant is positive, and I ask you to find the other 5 trig functions of theta. So what should we try to figure out first here, do you think? Which quadrant it's in. That's probably the best thing to try to figure out first, right? So tells you the secant is negative. So what's secant equal to in terms of sines and cosines? 1 over cosine, right? Where is cosine negative?
Quadrant 2 and 3.
Quadrant 2 and 3, right? So we know we're in one of these two, right? We agree? Okay, and that's because secants 1 over cosines, as it says the secant is negative, the cosine is also negative. So we have to be in 2 or 3. But we're also told that cosecant is positive. What's cosecant equal to in terms of sines and cosines? 1 over sine. If that's going to be positive, then what quadrant do we have to be in? 2, right? Okay. So our triangle here is going to be over here in quadrant 2. Everybody see why?
Yeah.
Yeah? Are you okay with that? All right. So it tells us the secant is negative 41 over 9. What sides then can we label from that? Yeah, the hypotenuse and the adjacent, right? So in particular, usually we like to think about it in terms of cosine, right? And you already told me that was the reciprocal. So what should I label the hypotenuse? Let's start there. 41, and it's always positive, right? Because we think about it as a distance from the origin. Okay. So then, what other side? You told me the adjacent. So the adjacent side we'll label as -9. Then we're going to do the Pythagorean theorem for the other one. So if I call this, say, B, for what lack of a better letter, what will the equation look like if I call that B?
A squared plus B squared equals 1 squared.
Okay. Let me give you another be careful, and this is a be careful with your calculator. Okay. If you're typing if you type in the negative with the 9, and you square it, make sure you put parentheses around the whole -9. The reason is that if you put -9 squared and literally just type that in your calculator, it's going to do the squared first and then take the negative. You don't want the negative anymore when you square it in this case. Okay. So be careful with that on your calculator if you're typing things. And that's just a general be careful if you've got a negative. If you're trying to square, make sure you square the negative too. Negative as well. All right, so let's see. -9 squared is 81. And 41 squared should be 1681. So your b squared will be 1600. Yep. So if I take the square root of both sides, what do I get? 40. Now technically, you get plus or minus 40, right? When you take the square root of both sides of an equation, you get plus or minus, right? Now, why is it that we want the positive in this case? Because the b is above the x-axis, right? Okay, so that's why we're going to use 40 over here. We want the positive, I'll write it down. We use positive 40 because our triangle is above the x-axis. That makes sense? All right. So now we should be able to get the rest of them. We already have cosine. Given the triangle now, what's the sine? 40 over 41, right? It's opposite the 40 over the 41. Okay. Tangent. Yeah, the 40 over the -9. And then we should be able to do the other ones just by reciprocal. Cosecant is 41 over 40, and cotangent is -9 over 40. Good. This one okay? Any questions on that at all? All right. Well, let's go on then and talk about some new stuff. So 6.4 talks about graphs of trigonometric functions. And what we're going to do in this particular section is get an idea of what the basic graph looks like for each of the trig functions, and then talk about how we can transform those graphs either by stretching or shrinking or shifting. Now you've done stretching and shrinking and shifting of graphs before this class. It's the exact same concept. It's not anything new. They just use different words, okay? But it's literally the same stuff, right? But first, let's concentrate on actually getting a graph for each of the trig functions. Actually, today I'm going to do sine and cosine. Ouch, I smacked my hand on that monitor. We're going to do sine and cosine, and then Wednesday we'll do the other four. Okay? So we'll do sine and cosine today, talk about what the graphs have to look like, talk about the properties of the graph, and do some transformations of those graphs, and then we'll talk about the other four, right? So just like what you did back when you first started learning how to graph back in Algebra 1 class, we're going to just take that same basic approach to get a graph for the sine and the cosine. We're just going to plug some numbers in and get some numbers out and plot some points. Okay? So let's say we had the function, I'll say f of x equals sine of x. I'm going to pick some numbers for x to plug in. I'm going to pick some good numbers for x to plug in because I want to be actually able to get some values out of this. So to start that, let's start with, let's say we do 0, pi over 6, pi over 4, pi over 3, and pi over 2. Now a couple of those, we haven't talked about the exact values yet, but we have talked about pi over 6, pi over 3, and pi over 2. Pi over 6 is the same thing as 30 degrees. What's the sine of pi over 6? If you think about the triangle. 1 over 2? Good. Yeah. So remember your 30, 60, 90 triangle. The side opposite the 30-degree angle is 1. Side opposite the 60-degree angle is root 3. And then the hypotenuse is 2. Right? Okay, so when we do sine of 30 or sine of pi over 6, we get a half. For pi over 4, in degrees, what's that the same thing as? 45. Is what the same thing? It's going to be 1 over square root of 2, right? Because that the 1 square root of 2 for the hypotenuse there. So this is 1 over root 2. For pi over 3, in degrees, that's the same thing as 60, right? So we're going to get what? Root 3 over 2, right? Now, the other two we haven't talked about for 0 or pi over 2, but... What's that? It's okay. Let's talk about what they should be. All right, so think about what happens just in a triangle in general. I'm just going to use the picture. If I make this angle get smaller and smaller in here, what's going to happen to the opposite side? It's going to get smaller, right? So if I make this angle keep getting smaller and smaller and smaller, the opposite side is going to get closer and closer to what? 0, right? So what do you think the sine of 0 degrees should be? 0. Yeah, exactly.
90 is 1.
Yep, and 90 is 1, exactly. So same idea for the other one. If we think about what happens as the angle gets bigger, closer and closer to 90, if the angle gets closer and closer to 90, this is going to get closer and closer to 0, right? Because I got to keep them equal, right? And if this one's going to get closer and closer to 0, that means this side's going to get closer and closer to 0, and these two sides will be the same. So we'll get 1. Okay. So at pi over 2, we get 1. So those are a couple of the angles we hadn't talked about. So sine of 0 is 0. Sine of 90 degrees or sine of pi over 2 is 1.
Wait, how do you visualize the pi over 2?
The way I would do it is think about what happens if, say you drew something like, well, let's say it's like this, just for the argument's sake. So let's say this is 80 degrees and this is 10, right? Notice that this side's getting really small, okay? And then if I do something like, this side's getting really, really small, right? What's happening with your boat, as this side's getting really, really small, what's happening with these two sides? They're getting basically the same size, right? And so that's why if we divide something by itself, we get 1. So those two are getting really, really close to each other. Does that make sense? All right. So that's the idea, as we shrink this side, this bottom side, these two get closer and closer to each other. And so you just get, that's why the opposite over the hypotenuse is 1. All right. So if we think about just plotting these points, let's just do those to start with on a graph. the points we're going to plot here, let's see, we're going to go up to pi over 2. We just said that we have the point 0, 0, right? X is 0 and the output is 0. We also have the point pi over 2, 1. So that'll be up here. Now let's think about where we put these other points. Pi over 4 is halfway between 0 and pi over 2, right? Pi over 4 would be halfway in between. And we said that that's equal to 1 over square root of 2. If you put that in your calculator, you get about 0.7. It's 0.707 and change. Okay, so that would be about up here. Pi over 6 is a third of the way over here. So it's about right here. Okay, so pi over 6. The reason I know it's about a third of the way over, closer to the 0 is because, remember, pi over 4 is 45 degrees. Pi over 6 is 30 degrees, so I subtracted 15 degrees off, which is a third of 45. That's how I do it. It was about a third over. And we said that was equal to a half, which would be about right here. And then we can do the same thing for pi over 3. It's just on the other side of pi over 4. And we said that that was square root of 3 over 2. And if you check your calculator, that's about 0.866. So about here. So we have those points. So if we were to graph this, then this would go something like so. Just playing connect the dots, making it smooth, right? You agree? All right. So now we want to see what, but we don't want to just do from 0 to pi over 2. We want to get a graph for any x that we could plug in, right? So let's say we do the next set of these. Oops. So let's say we had x and f of x. We put in 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. Now, why did I pick those numbers? Let's think about why I picked those ones. Okay, so they're definitely between. Yeah, this is sine. Yeah, so 2 pi over 3 up to pi are definitely between pi over 2 and pi, right? So what I'm thinking about doing, if I think about rotating around here, right? We did these as we got to here, right? And then I want to keep going around this way, right? Keep going. That's the idea. Now, what are the reference angles for these particular values that I picked? What's the reference angle for 2 pi over 3? Pi over 3. And for 3 pi over 4? Pi over 4. And for 5 pi over 6? Pi over 6, right? Those are the reference angles. We already know what those values are. So, since the reference angle is pi over 3, what's the sine going to be? So it's 60 degrees is the same as pi over 3, so the sine of that will be it's right there, right above, right? We already did that one, didn't we? Right? Is it positive root 3 over 2 or is it negative root 3 over 2? Positive, how do you know? Because it's in the second quadrant, right? We know it's positive root 3 over 2. What about for 3 pi over 4, what's it going to be? 1 over root 2, or if you prefer, that's root 2 over 2. Either way, I don't care how you remember it. For 5 pi over 6, 1 over 2, yeah, the half, right? What do you think it's going to be for pi? Well, let's think about, just think about the picture first. Let's go back up to the picture. At 2 pi over 3, all right, so at 2 pi over 3, we had that root 3 over 2, right? We're right here. At 3 pi over 4, we had 1 over root 2, which is right here. Pi over 6, 5 pi over 6, sorry, we were at a half. What's it look like this graph is doing? Going back down to 0, right? So our sine of pi really is 0. So we end up with that part of the graph. So far, so good? All right. So need to go a little bit farther here because I haven't gone around the whole circle, right? I haven't gone all the way around, have I, to figure out the different sines and cosines, right? We went from here to here and then from here to here. Let's do the next quadrant. So we have x and f of x. All right, so I probably want to do some pi over 6, a pi over 4, a pi over 3, and a pi over 2, right? Using those reference angles, because we know the signs of those reference angles, right? Now, what are those numbers that I left a little space in the numerator going to be? Well, let's think about it. I want to start at pi and move it another 30 degrees, or start at pi and move it another pi over 6. What angle is that going to be? 7 pi over 6, right? Pi is the same thing as 6 pi over 6, we went one more click, right? Essentially. So 7 pi over 4, 7 pi over 6, I said the wrong thing. All right, let's think about it. How do I get to the next pi over 4? Well, here to here. So how many pi over 4s would pi be? 4 pi over 4, right? And one more gives me 5. So what's the next one for the pi over 3 going to be? 4 pi over 3. And for the pi over 2? 3 pi over 2. Okay. Now let's think of the values. Well, we just said the reason why we picked these is because we know the reference angles, right? The reference angle for the first one's pi over 6. What's the sine of pi over 6? 1/2. But what quadrant are we in? Third. So what needs to go out in front? Negative. For 5 pi over 4, then what are we going to get? Negative 1 over root 2. For 4 pi over 3? Negative 3 over 2. And what do you think for 3 pi over 2? What are you going to get? Well, what was the sine of pi over 2? 1, so it better be negative 1, because we're below the x-axis, right? So if I go back up over to my graph, scroll over and down a bit here. So we had negative, my negative 1's not in a good spot, is it? Let's move this. I'll erase the whole axis. Of course I did. Oh, now it's in red. Just a mess. All right, try this again. So pi over 4 again was right in the middle, so a little bit less than that gives me 1/2, negative 1/2. Pi over 4 would give me negative 1 over root 2. The 4 pi over 3 would give me negative root 3 over 2, and at 3 pi over 2 we would have negative 1. So if I play connect the dots again, seriously, I hit the black. Look at that. And now we could plug in the values, but you can probably guess what's going to happen for the next part. We went up and went down. Now we've gone down. What do you think is going to happen? Go back up again, right? So at 2 pi here, we will get that part. All right, so hopefully it makes sense why these values here correspond to what quadrant? These x values here correspond to what quadrant? First quadrant, right? So this means that they were all positive, correct? This corresponds to quadrant 2, they're still positive, right? This one's quadrant 3, they're negative, and then quadrant 4, they're still negative. Okay? And then think about, as you rotate around, what's happening to that opposite side. As I go up, the opposite side gets bigger, and then it gets smaller. Okay? So that's how we're getting the bigger and then the smaller. So notice that this is only from 0 to 2 pi. I said we want to get a graph for the whole thing. Well, what happens once you get around to 2 pi? It's going to do the exact same thing again, right? Until I get to 4 pi, and then same thing until I get to 6 pi, and so on down the line, right? So if we want to get a whole graph of this thing, so if I have, I'm going to shrink it a little bit so we can see it. All right, so we know that halfway in between 0 to pi, we're up at 1, right? Because that's pi over 2. And halfway between pi and 2 pi, we're down at negative 1 because that's 3 pi over 2. So that was what we just graphed a minute ago, right? We went up, down, and back up again, right? And then you said it's going to repeat itself. So I should draw that exact same shape from 2 pi to 4 pi. So I'll be up here at 1, back down here at 0, back down here at negative 1, back up here at 0. So you get up, down, and back up again. And if you wanted to go from 4 pi to 6 pi, you would draw the same thing. 6 pi to 8 pi, draw the same thing. And you can go to the left as well, right? So it should look the same over here. From negative 2 pi to 0 should look the same. From negative 4 pi to negative 2 pi should look the same. So this is what your graph of sine of x looks like. So this is your basic graph for sine. This is something that you should be able to visualize, not just this semester, but going on to calculus, because you'll be asked to visualize this in calculus as well. Okay? It's a very, very important graph to remember. From a modeling perspective, the trig functions, especially sine and cosine, are important for modeling repetitive behavior, temperature, waves, those kinds of things. If you're doing electromagnetic waves or any of those kinds of things, trig functions model those things because of that repetitive nature, right? Think about what temperature does over the course of a year. It goes up and down and back up again, right? So the kind of idea, that this idea of being able to bounce up and down is an important one that pops up in lots of different applications. All right, so let's talk about some different properties here. Do we see any holes in the graph anywhere? If we continued on, do we see any holes? Do we have any problems with plugging in a number for x? No, okay. So one of the things that we notice is that the domain here is all real numbers. One of the things you should get used to, if you're not already, is interval notation. So all real numbers we can denote with the interval from minus infinity to infinity. That just means that no matter what number we pick, we can always take the sign of it. Doesn't matter what the number is. How about the range? What are your y values that you see coming out of this function? Negative 1 to 1, right? Does it actually hit 1 and hit negative 1? Do we get those numbers out? Yes. Okay, so do we use a parenthesis or a bracket? Bracket. Good. You guys are all over this. All right. Let's do y-intercept first. That one's easy. Where does this thing cross the y-axis? Yeah, it's 0, right? So it's the point 0, 0. All right, how about x-intercepts? Where does it cross the x-axis? Yeah, 0 and at 4 pi, and at negative, right? We had lots and lots and lots and lots of x-intercepts, right? So we write this as ordered pairs. Certainly the y-coordinate is 0 for any x-intercept, right? We write this typically as an n times pi. where we say n is any integer. So integer, again, just means a whole number that could be negative, right? No decimal part. Okay, so you get 0. So if I put in 0 for n, I get 0, 0. If I put in 1 for n, I get pi 0. Right? Those are the points that I'm talking about. So it crosses the x-axis at the multiple. X is a multiple of pi. Does that make sense how I wrote that? Okay. We'll write things like this quite a bit this semester, so it'll make more sense as we go along as well. All right, so there's one more thing that I want to mention for this particular property. Well, actually there's two more things, but the first one I'm going to mention is this one. It's the period of the function. The period means how long does it take for the function to repeat itself. So how long did it take in x terms? How long did it take to start repeating itself? Well, it hasn't started repeating itself yet until I get to here, right? So then it repeated itself, right? How long is that interval? 2 pi, right? Which is the same as going all the way around the circle. So the period of this function is 2 pi. Okay? Okay so far? All right. The last thing that we mentioned is what's referred to as the amplitude here. In general, you calculate your amplitude as for that basically it's only for sines and cosines. It's always your high value minus your low value over 2. And if we're trying to read it from a graph, it's exactly what we would do. But it's how high up does it go, how low does it go, subtract those two numbers and divide it in half. Basically, it's a displacement idea. Notice here the high value is 1 and the low value is -1. So if I subtract those, I'll get 2. And then divided by 2, I get 1. It's a displacement idea. Do you kind of see that the x-axis here is in the middle? So it goes up 1 and goes down 1 from the middle. That's the amplitude idea. So for this case, the amplitude is 1. And that'll be the same for cosine as well. Now again, we're going to talk about how we do transformations of these things. In particular, when we do transformations, we'll talk about how it changes the amplitude in the period. We'll talk about those as we get to it. But any questions on how we arrived at that particular graph? And were you okay with the properties that we just wrote down? Well, let's do the same thing for cosine. I'm just not going to spend all the time calculating points. I'm just going to draw the graph here. Oops, maybe I'm going to draw the graph. All right, so for your function f of x equals cosine of x, let's think about, I'm just going to get a few values here. Let's do pi over 2 pi, 3 pi over 2, 2 pi. All right, so certainly we know that from 0 to pi over 2, we're in quadrant 1, right? So we know we're going to be above the x-axis. But we also know that, from lots of different ways how we can get these values, but we know that the cosine is the co-function for sine, right? We agree? So in particular, if I want cosine of pi over 2, what's the complement of pi over 2? 92 is pi over 2 is the same thing as 90 degrees. What's the complement of 90 degrees? Be 0, right? Because I have to add up to 90. So if I want the cosine of pi over 2, I can look at the same thing as the sine of 0, which was what? 0, right? So I'd be down here. How about the complement of 0? What would be the complement of 0? 90 degrees, and what was the sine of 90 degrees? 1, so it would be up here. Now, there are other ways to get these values. I was just trying to reinforce that co-function idea, right? Okay. But in particular, we're going to start up here at 1 and come down here to 0. And we're going to have a similar shape as we do for sine. It'll come down like so. From pi over 2 to pi, what quadrant are we in? The second. And what do we know about cosine in quadrant 2? Negative. So it makes sense that we're going to cross the x-axis and dip below, right? If the cosine is negative, the graph of this function better be negative, correct? Below the x-axis. So it's going to come down here to -1 and bottom out. From pi to 3 pi over 2, what quadrant are we in? Third. So it better be still negative, right? But by the time we get to 3 pi over 2 and go to 2 pi, it has to be positive. So we better cross the x-axis at 3 pi over 2 and then back up to 1 at 2 pi. So this is one period of the cosine function. Because once we get to 2 pi, we're essentially back at what? 0, right? We're rotated back around again, right? Okay? So at this point, if we want to get more periods, we can just redraw it. So let's say we had, say this is pi over 2, negative pi over 2, and negative pi, and I ran out of room, here 3 pi over 2. It would come down and back up and top out over here again at 2 pi, negative 2 pi. We can continue out this way. If I had 5 pi over 2 and 3 pi and 7 pi over 2. Oops. Scroll. And 4 pi. It would come down and then bottom out and go back up and top out. Just repeats itself every multiple of 2 pi, right? So again, let's write down the important information for these. What's the domain here for cosine? Any numbers we can't plug in? No, so what do we have? All real, yeah, all real. So negative infinity to infinity again, right? How about the range? -1 to 1. And again, we include those, correct? Y-intercept? Yeah, it's the 0.01, right? X-intercepts are a little trickier to write, I mean. Well, certainly the y-coordinate for any x-intercept is what? 0? All right, so let's look at these for the x-intercept. Pi over 2 is one of them, right? And almost. Good idea. Almost. Pi over 2 and 3 pi over 2, right? And 5 pi over 2. How far apart are they? It's a pi apart, right? So to get from one to the next, I have to add pi. So it's going to be pi over 2 plus again. There you go. Yep, so I have to, if I start with one of them, say pi over 2, I have to add multiples of pi to it. So it'll be pi over 2 plus n pi. How about the period? How long did it take to repeat again? 2 pi. And how far up does it go from the middle? 1, right? How far up or how far down? So the amplitude here is 1. Does that make sense? Still write it down. Gotcha. All right. So again, those are the basic shapes for sine and cosine. And again, you're going to want to get those committed to memory because you're going to work with these. Of course, if you don't have them necessarily committed to memory, you can always look at them on your graphing calculators too. So let's see what happens. Let's do a change in one of these, because that's one of the things we'll be interested in is transformations. So let's say I wanted to get a graph of, this is an example here. Say I wanted to get a graph of y equals 2 sine of x. All right, so what we're going to be doing is transformations. And again, the whole point of this is to attack it like you've done in the past, and just use the language of trig functions when we are answering questions. But basically, we're going to attack this like you do in any other algebra class that you've done where you've done transformations. You're going to start with your y equals sine of x graph. So y equals sine of x, I like to think of it as a starting point. The y equals sine of x starts at 0, 0, right? And then goes up, comes back down, goes back up, right? And then it does the same thing on this side. Oops. Sure it does. Pardon me. That's your original graph, isn't it? Okay. Let's think about this 2. Is that on the inside of the function or is it on the outside of the function? It's on the outside, right? So think about it. If I plug a number in for x, the first thing you're going to do is get the sine of it and then multiply it by 2, right? So does that affect the inputs of sine, or does it affect the outputs of sine? Outputs. So is it going to affect the x coordinate or the y coordinate? The y. And what's it going to do to all the y coordinates? Well, it's going to double. It's going to multiply by 2, right? You know the easiest way to handle that when you're graphing it? Watch carefully. There you go. I handled it. I just multiplied all the y coordinates by 2. It's all it does is change the scale, right? Literally all it does.
So, but what if it was sine of 2x?
Then we have to do something different. We'll talk about that on Wednesday. But yep, you're right. Okay, so we're sine of 2x, we have to do something different, but what do you think it would affect, the x's or the y's? X's, because it's on the inputs, right? Okay. All right, so one last thing to mention on here. Notice that we changed the scale. We changed the y scale, right? So which of the things that I wrote here above, it changes the amplitude, right? So instead of 1, what's the amplitude going to be? 2. Yeah, so the amplitude here would be 2. And it changes the range as well, yep. All right, so what will your range be? -2 to 2? Good. So it changes that amplitude, right? Okay. We'll do more of these next time, as well as get into the other 4 trig functions. Have a good one. We'll see you then.